Okay, cool. Let's get started. So, okay, it's kind of complicated, right? Like, it's kind of amazing, right? Like this technology is so advanced so that you can do all of these things together, but still you have to do them one by one. Like I have like 10 action items, or maybe more than 10. I need to also connect to the Wi-Fi. That's actually something I have to do. Okay, so but let's get started. Oh, I need to have my notes. So what we're going to do today is that we are going to continue with the asymptotics last time a little bit for like about like 15 to 20 minutes. This is just to wrap up what we have discussed. And as I said, this first lecture is always kind of like a little bit tricky for me to teach it because the tools there, if you want to make it formal, it requires some kind of backgrounds. And if you don't want to make it formal, sometimes there is a little bit of confusion. So from this lecture, the second half of this lecture, I think we're going to talk about things that require less background in some sense, and it's more self-contained. Okay, so the plan is that asymptotics, and then the so-called uniform convergence. I'll define what it is. And uniform convergence will be the main focus for the first few weeks of the lecture. Okay, so let's start by reviewing what we have done last time. So what we have the last time was this theorem where we showed that if you assume consistency, which is something that is kind of like we basically just assume without much justification, it's not always true, and it also depends on the problem. The consistency basically means that theta hat will converge to theta star. Recall that theta hat is the ERM, the empirical risk minimizer, and theta star is the minimizer of the population risk. So you care about recovering theta star or recovering something as good as theta star. And we also assume a bunch of other things, like, for example, the Hoeffding is full rank, and also some regularity conditions, which I didn't even define exactly. For example, this requires something like some of the variance is finite, so you can apply the theorems. And then under these assumptions, we have that. Actually, it's kind of challenging for me because this podium, after I raise it, it becomes unstable. It's kind of like I feel like I'm writing when I'm on a boat. That is probably good for me to practice my kind of like what is this called? Like I will be better with some of the sports, I guess, after we do this. Anyway, okay, so so I guess we have discussed that that the distribution, the order of the difference between theta hat and theta star. The order is on the order of 1 over square root n. And formally you write it like this. You scale by square root n, and you know that it's on the order of 1. And you also know something about the laws. You know that the excess risk, L theta hat minus L theta star, is on the order of 1 over n. And if you formally write it, you're going to scale by n, and then you say it's on the order of constant. And also you know that the distribution of theta hat minus theta star, this is converging to a Gaussian distribution with mean 0 and some covariance. And this covariance is kind of complicated, but let me write it. Something like this. This is just reviewing what we have written last time. And 4, we also know the distribution of the excess risk. This is a distribution of a scalar because the excess risk is a scalar. If you scale it by n, then you know the distribution is converging to the distribution of this random variable. And this random variable S is a Gaussian random variable with covariance mean 0 and covariance something like above, but not exactly. You don't have to remember exactly what the covariance here is because I don't even remember them if I don't read my notes. These are, there are some intuitions about this which I'm going to discuss, but generally this is just was something you got from derivations. So last time we have kind of like roughly justified the number 1, number 2, and today I'm going to again give a relatively heuristic proof for 3 and 4, just very quick, so that we can wrap up this. So I guess just to very quickly review what we have done last time. So the key idea to kind of like derive all of this is by doing Taylor expansion. And Taylor expansion, I think the key equation, let me just rewrite it, what we have done last time is this. So you look at the theta hat, the gradient of the empirical loss at theta hat. This is guaranteed to be 0 because theta hat is the minimizer of the empirical loss. And you Taylor expand this around theta star. And you get something like this. Plus higher order terms. And then you rearrange this and get theta hat minus theta star is equals to the inverse of the empirical Hessian at theta star times nabla L hat theta hat plus higher order terms. And then you say that I'm going to replace all the hat by L, like L hat by L, using some kind of law of large number or uniform convergence. And last time we have roughly discussed that this is on the order of 1 over square root n because you have a concentration. This is the average of, this is roughly on the order of 1 over square root n plus nabla L theta. Sorry, this is theta star. L theta star, which is roughly on the order of 1 over square root n. And this one is converging to a constant. So that's why the whole thing is converging to something on the order of 1 over square root n. And this time we are going to make it a little bit more formal. So to get the exact distribution of theta hat minus theta star, I'll make this part really quick, just so that if you are not familiar with the background, you don't get confused too much. So the idea is that if you look at what's the distribution of this, if you think about this, this is the product of two random variables. And you roughly know what the distribution of each of the random variable is, right? So this one is going to converge to a constant, which is going to converge to nabla L theta star inverse. And this one is going to be a Gaussian distribution if you scale it correctly, right? So, and basically what you need to know is that what's the product of these two random variables? What's the distribution of the product of two random variables? When you know each of them, what happens with each of them? And what happens is, formally, what you do is you first scale by square root n, so that each of these two random variables are on the order of 1, so that you can reason about them easily. So you scale by by square root n, you get this, and then you have inverse. And now you scale this empirical gradient by square root n, and also you get square root n. And also let's fill in the population gradient, which is 0. So this one is 0. I just write it here to make it closer to something you know. And then this plus higher order terms. This is still higher order terms even you multiply by square root n, because I think there's a typo in the lecture notes somebody pointed out, which is really nice. But still, no matter how you multiply, it's still higher order terms compared to the other terms, right? So, and now this one, let's call it z. This z by law of large number, or I think by central limit theorem, z is a Gaussian distribution because and with some covariance. And what's the covariance? The covariance will be the covariance of nabla L x y theta. Why? This is just because what is L hat theta star minus this? This is really just this is the empirical version of the right hand side, the population gradient. So this is really some 1 over n times sum of nabla L xi yi theta star minus expectation of this, right? Of the same thing. Maybe you can, for simplicity, let's just write xy theta star, right? So you apply this, you apply central limit theorem. You know that if you scale this by square root n, then you get a Gaussian distribution, right? So that's why we know the random variable z has Gaussian distribution, and we know this one will converge to a constant as n goes to infinity. And there is a theorem that specifically deal with this, but actually, if you think about it, this makes a lot of sense. So if you want to know what's the left-hand side, basically it just becomes the distribution of the right-hand side. It's a constant times a Gaussian distribution. This constant times a Gaussian distribution. So basically, we have to figure out what's the distribution here. So like, what is the distribution of a constant times z? So so basically, abstractly speaking, what we are dealing with here is that. So the question we're dealing with here is that. Maybe let's just. So a different color for abstraction. So basically, you are asking what is the distribution of A times Z if A is a constant and Z is from some Gaussian distribution with covariance sigma, right? So, and somehow I'm missing a page. And you know that there's a lemma which says that if under this case, A and Z is also a Gaussian distribution with covariance with mean 0 and covariance A sigma A transpose. I think this is a homework 0 question. I'm not sure whether it's still there. I forgot to double check. This is something you can do. Like what's the transformation of a Gaussian distribution? Still a Gaussian distribution. It's just the covariance got transformed. And actually, the way to transform the covariance is that you left multiply the transformation and right multiply the transpose of it. You get a new covariance. So this is something, it's not that trivial to derive this, but this is something you can either look up from a book or you can derive it yourself, right? So with this small lemma, then we know that the distribution of theta minus theta star converges to converges to a Gaussian distribution with mean 0, where A, so here A corresponds to the nabla L theta star, right? And sigma corresponds to this one. And you just plug in these two choices, then what you have is this, basically what we intended to prove. We got nabla square L theta star minus 1 times covariance of nabla L x y theta star times nabla L theta star inverse. Okay, this is convergence in distribution. Any questions so far? I realized that my camera is frozen. I don't know why. Something seems to be wrong. For those people who are on a Zoom meeting, can you see my video?
It's kind of frozen.
I see. Thanks. Maybe let me turn it off and then turn it on. Okay, sounds working now. Okay, cool. And you can see iPad. You can see everything now. Okay, thanks. Okay, cool. Any questions? Also, if you're in a Zoom meeting, also feel free to just unmute and ask any questions.
So at the end of the variance at the end, that's a Gaussian, and then it's a negative theorem.
This is inverse.
Yeah. Like the variance.
Sorry, which term are you asking? This one?
The one next to this.
Here?
The one to the right.
Yeah, this is the same. Yes, it's exactly the same one. It's supposed to be the same thing transpose, right? But this is a symmetric matrix. So the transpose is the same as self. So this is -1. Okay, so I guess what I'm going to do is I'm going to skip the proof for the derivation for the number 4. It's kind of like the same thing. It's just that you have to kind of like, because you already know the distribution of theta hat, you should know the distribution of L of theta hat. And what you do is you do some Taylor expansion to make it a polynomial of theta hat, and then you can use the what you know about theta hat. All of this in lecture notes. I guess I'm going to skip this part.
So we wrote that it looks like, for example, like the Newton's method update. Is there a reason for that?
You mean the covariance seems to be like the new?
It's just like the step of the gradient direction modulated by the intersection. Like that'd be a Newton's method update.
Mm-hmm.
Is there a connection between the two? Or?
I think there's a connection, but I don't feel like is I think all like this Hessian shows up very often in many different cases, right? So there is some connection, but I don't feel like it has to be like, it's not like super closely related so that it's important enough to know. Yeah. Okay, so I guess I'll skip the proof for number 4. If you're interested, you can look at the proof in the lecture notes. And what I'm going to do is that I'm going to spend another 5 to 10 minutes to talk about a corollary of this theorem, which is in a more maybe a more typical setting. Like here this theorem is very general because it doesn't say anything about the loss function. It doesn't say anything about the model. It works for almost everything as long as you have the consistency. And here, let me instantiate this theorem for the so-called well-specified case where you use log likelihood. And then we can see all of this covariance becomes a little bit kind of like more intuitive, and things becomes a little bit easier. So this is the so-called well-specified case. So I guess in addition to theorem 1, let's also assume that, let's suppose there exists some probabilistic model parameterized by theta. So such that y is given x and theta. So you assume that y is generated from this probabilistic model, right? So what does it mean? So basically it means, so let's say suppose there exists a theta star. I'm using the subscript here to differentiate from the theta star defined before, which was the minimizer of the population risk. And actually they are the same, but for now they are the difference. So basically you assume that there exists a theta star such that the yi, the data, is generated from condition xi is generated from this probabilistic model. Right. So you assume, so this is why it's called well specified. It means that your data is generated from some probabilistic model. And also in this case, suppose you use the loss function is the log likelihood. Right. Before we didn't really say what the loss function needs to be. Right? It could be anything. And now let's say the loss function is the log likelihood of this probabilistic model. Think of this as, for example, logistic regression, right? Or linear regression with Gaussian noise. So your log likelihood could be cross entropy loss, could be like mean square loss, depending on what the probabilistic model you have. Right. So this is your loss function. And when you do this, then you know a bunch of things which are nicer in some sense. So first of all, you know that the theta star is equals to the theta substar, right? So recall that this is the minimizer of the population loss. And this is the ground truth. This is the one that generates your data. And in this case, you can prove that when you have infinite data, right? Theta star is the minimizer of the infinite data case. You can recover the ground truth, theta substar. So they are exactly the same thing. And you also know a bunch of other things. For example, you know that the gradient this is kind of trivial. I'm just writing it here because it used to be that I need to prove this in the proof. But if you don't care about the proof, this is just an intermediate step that you know. So you know that expected gradient over the population at theta star is 0. And also you know what's the covariance of the gradient. This is the covariance of the gradient is the quantity that we care about, right? Because in the previous theorem, the covariance of the gradient shows up in the variance of theta hat minus theta star. So the covariance of the gradient is at theta star. I guess from now on we don't distinguish theta superstar and theta superscript star and theta subscript star because they are the same. And the covariance actually happens to be the Hessian. And when the covariance of the gradient happens to be the Hessian, then the covariance of theta hat minus theta star can be simplified. So this, recall that this used to be a Gaussian distribution with something like this, right? The covariance of the theta hat minus theta is used to be this product of three matrices. But now what's in the middle is the same as the Hessian. That's what we claimed in number 3. So that means that you can cancel this with this, and you get only one term. So what left is that just the inverse of the Hessian. Maybe I should just use black forever. Yeah, and you also know if you plug in, like the covariance of the gradient, you basically plug in 3 into all the statements that you had before, then you can also get something like, for example, one of the important things is this. The excess risk, I guess we have claimed that it's on the order of theta star, but actually here you can be more precise. You know that this is converging to basically a half times chi-square distribution of with degree p. So p is a dimension of theta. So suppose you have p parameters, then this is the distribution of the excess risk. And if you take the expectation of this so that you get all the randomness, then what you get is the expectation of n times excess risk is equals to the expectation of the chi-square distribution. That this is equals to a half times p. By the way, chi-square distribution, if you don't have to know anything detailed about it, this is basically the distribution of a sum of p normal Gaussian square. So you know a lot of things about it, like it's positive, and you know that its mean is like if the chi-square with degree p, the mean is p. If you need to know more about this, just Wikipedia. It's very easy. We don't need anything deep about it. So the important thing is the last equation. So basically, we know that the excess risk in expectation, here the expectation is over the randomness of the data set. Right. So the excess risk, if you don't scale by theta star, if you don't scale it by n, then you get this is equals to, I guess I should write converging to, because it wouldn't be exactly equal. This is a half times p over n. So basically, you don't even get the dependency on n, but you also get a dependency on p. So on a dimension. So you know that what's the order of the excess risk. Of course, there's a high order terms made of 1 over n. And actually, you even know the variance of the excess risk, which I don't think is super important. The variance is smaller than the mean. Okay. So in the lecture notes, I think we have proofs for all of this. But I think I'm not going to discuss the proof. The most important thing I think is this one and this one. So the first thing is saying that the shape of theta hat minus theta star, the randomness is the shape is kind of like the same as the inverse of the Hessian. So in those directions where your Hessian is steeper, then you have less stochasticity, right? So and in those directions where the Hessian is smaller, then you have more stochasticity. And the last one is saying that it doesn't matter what Hessian is, the only thing that matters is the number of parameters. If you care about this kind of like asymptotic regime, the only thing that matters is the parameter p, the number of parameters. We're going to discuss the limitation of all of these theorems in a moment. But this is what we got from this asymptotic approach. Any questions so far? Okay, cool. So I guess let's, if you are interested in more details, you can take a look at the lecture notes. So I guess now let's move on to uniform convergence. Often people call this kind of line of research called non-asymptotic. So let's first discuss that. This is actually the kind of like the approach that we're going to take for the rest of the lecture. We're going to care about non-asymptotics instead of asymptotic bounds. So the reason, so let me define, let me motivate define what it is and motivate why we care about it. So recall that when you have asymptotic bounds, just that's like what I wrote above, you know that this L theta hat minus L theta star, the final outcome is something like this is equals to P over 2n plus lambda of 1 over lambda of 1 over n. However, the problem is that here you are hiding a lot of things in this lambda of 1 over n. So you hide all dependencies other than the dependencies on n, other than n. So what does it mean? So in this little O notation, you also have dependency on P. So if you tell me in asymptotic regime you get this bound, what happens is that you could either have P over 2n plus 1 over n squared. Maybe the real rate is this. It could also happen that the real rate could be this. So both of these two cases would be a possible situation if you tell me the bound above, right? I wouldn't have ways to distinguish this because this one is hidden in this little O notation, because the little O notation doesn't care about any dependencies on anything else. It only cares about the dependencies on 1 over n, at least in the context of asymptotics. So this is the problem, because clearly if your rate is on the right hand, is something on the right hand side, then this is very bad rate, right? Very bad. By the way, by rate I mean the how does this depend on how. I guess maybe let's just call it bound, right? So suppose your bound is on the right hand side, then it's a very bad bound, because this requires n to be bigger than p to the 50, so that this bound is smaller than 1, right? Because you need a second term to be smaller than 1, then you need n to be bigger than p to the 50.
So this is where the rigorous definition of little o over n. Does that mean that n times the function goes to 0 and then goes to infinity?
Yes. Yeah. So exactly. Okay, and going back to this, so the bound on the right hand side is going to be very bad, and the bound on the left hand side, this one, is kind of pretty good in some sense, right? But you have no ways to distinguish them, because these two things would be counted towards p over 2n plus lambda of 1 over n in the asymptotic sense. So that's the biggest problem, and also in some sense, when you have other dependencies on for example, the dimensionality, even the dependencies on n is not the only thing that matters. For example, another kind of like a more extreme situation is that suppose you compare p over square root n versus p over 2n plus this, right? Suppose you have two of these bounds, and if you use asymptotics, right? If you write in the asymptotic way, then you're going to conclude that this is p over 2n plus lambda of 1 over n in the asymptotic language, and this one will be something like p over square root n plus lambda of 1 over square root n. So it sounds like this is bad because this one has higher order dependencies on n, right? it's indeed true. When n goes to infinity, the right-hand side is smaller than the left-hand side. But if you think about a more moderate regime of n, then it's not really true, because for the bound to be less than 1, right? So if you want p over square root n to be less than 1, this means that n is bigger than p squared. But if you want this p over 2n plus p 100 n squared to be less than 1, this means n is to be at least equals larger than p to the 50, right? So when n goes to infinity, then the left-hand side, is worse, is a worse bound. But in most of the cases, the left-hand side is actually a better bound. So if you want the left-hand side to be a better bound on the right than the right-hand side, I guess if you solve this, maybe you can even ignore this. If you solve this, this is kind of roughly saying that if n is smaller than, I think I did this calculation at some point. If n is smaller than n to the p to the 66, then actually the bound on the left-hand side is better than the bound on the right-hand side, just because this p to the 100 is too big, right? So basically the comparison, basically if you use this asymptotic language, things becomes a little weird if you consider other dependencies on other parameters. For example, if you have a dependency on a dimension, and the dimension for machine learning, for modern machine learning, is very high. So this is why I think asymptotics, even though they are very powerful, they don't necessarily always apply to the modern machine learning, just because it has the dependency for other terms, right? In the high order case, right? So like this one has the dependency on p. So that's the main issue basically. Okay, so what we do, how do we fix this, right? The first thing we need to do is to fix the language in some sense. We need to not only consider n goes to infinity, we have to also consider other quantities in this world. So basically what non-asymptotic does is that you care about, this is just a term or kind of like approach. This is basically saying that you only had absolute constant in your bound. You have to hide something, because if you have to care about every constant, it's going to be too complicated for theory, right? It's going to be a lot of calculations. But here we allow us to hide absolute constant, but we cannot hide any other dependencies on any other things. So you're not allowed to hide dependency on p when n goes to infinity. So, and by absolute constant, this really means that this is a universal constant, like something like 3, 5, something you can replace by a real numerical number. And actually, to kind of like make everything easier, so we are going to introduce this notation, big O notation. This is actually, sometimes this big O notation has a little bit different interpretation. So I wouldn't say I'm redefining it, but I'm going to just be clear about what the big O notation means from now on. So now big O notations from now on only has universal constant. And let me have actually a kind of like more technical definition, which is actually useful in some cases. When you really do a lot of theory, sometimes, I'm not sure whether some of you have this confusion about whether you should use big O or omega, like the big omega. Like sometimes it could be confusing. So let me define what this big O really means. It really means that, so every occurrence, at least this is what it means in this course. It may not be exactly always the same for every paper, but I think people are converging to this kind of interpretation. So every occurrence of big O of x is a placeholder for some function, as a fx, such that for every x in R, fx is less than cx for some absolute constant c bigger than 0. So basically, this is saying that if you replace, so maybe more explicitly, it's saying that you can replace all occurrence, replace O of x by fx, such that the statement is true. So so basically, if you see a statement with a lot of O of x, O of something, right, it means that you can replace all of these occurrences of big O notations by something more explicit, such that the statement is still true. So it may seem to be overkill as a definition of big O, which you're probably already familiar with. But in some cases, at least I've seen so many cases where I got confused. I have to kind of really literally verify whether I satisfy this definition. Anyway, okay. So and also just for notational kind of convenience, sometimes we also write A is less than B. This is just equivalent to there exists absolute constant C larger than 0 such that A is less than C times B. And technically, if you really want to be kind of like very solid, this statement should only apply to positive A and B. Positive A and B. Because for negative ones, you have to, you probably, ideally you should just write this only for positive A and B. That's my suggestion. Because for negative ones, it just becomes a little bit confusing. So the point here is that there's no, like, when you define this big O thing, right? So it depends on the literature. Sometimes when people define big O, they have to define some limit. But here in this course, the big O just really means this. There's no limit taking. You don't have to think about any limit.
So are A and B functions here? Because A and B are positive numbers, and every number is less than every other number.
Right. So A and B could be functions or other more complex quantities. Okay, cool. So these are just some notations to. Okay, so now the kind of the bound that we care about is that. So we are interested in this notation. We are interested in bounds of the form like the x asterisk. So such you bound x asterisk L theta hat minus L theta star by something like big O of some function of maybe P and N, where P could be a dimension and N could be the number of data points. Of course, you can replace this by a function of other things. But the point here is that after you write this, there's nothing else hidden in a big O, only a universal constant. And this will once you have this kind of language, you can compare things in a more proper way. And in the next few lectures, our goal is to basically show how to provide bounds of this kind of form. Sometimes the bound could be more complicated, not only depending on the parameters, number of parameters and number of data points. It could depend on the norm of the parameters and so forth. But the point is that we always only had universal constants. Okay, any questions? For some, yes, that's very important, because if you replace it for all, because here there's also a, like, no, I think it's for some. So you literally only need existence of one function that satisfies this, such that if you replace that, if you replace your statement by f of x, the statement is true. So yeah, I think this is actually a very good question, because I got confused by this many times. So maybe let's give an example, right? So you say the x asterisk is less than O of 1 over square root n. What does this mean? This means that you can replace this. This is your fn, right? You can replace this by, for example, 5 over square root n, such that this is exactly true. But you don't need to say that for every f, right? So if you say for every f, then it means that if you replace by 0.1 over square root n, it still has to be true, right? That's too much, right? You only need existence of 1. But of course, if you have existence of one f, then there's always other f, which is bigger, that can also be replaced. But you only need one of them. And also, actually, maybe this is a little bit advanced, but this kind of like interpretation also allows you to have big O in your condition even. For example, you can, this could be a little bit advanced, but for example, you can write for all, like when if n is bigger than O of P, then excess risk is less than 1. This is, I'm not saying this is a correct statement, but this statement would be interpreted as if you replace this O of P by 2P, then it's going to be correct. Or if you replace this O of P by some function, some constant times P, it's going to be a correct statement. And it's not omega here. It's really big O, which is sometimes confusing. Okay, cool. So now let's move on to the key idea that we're going to have, right? So to bound this excess risk, how do we achieve bound like this? The key idea is to somehow say that L hat theta is close to L theta, right? In some way, in some sense. This is I need to specify what I really mean by these two functions are close, right? Are they close at every theta, or are they close at a specific theta? So here is a small claim which tells you what you really need. So what you need is that, so suppose L hat theta star is close to L of theta star. Suppose these two loss functions, empirical and population loss, are close at theta star. And also suppose they are close at theta hat. And here actually only need one set closeness. So suppose you have both of this, then this implies that L theta hat minus L theta star is less than 2 alpha. So basically, you just need to show that these two loss functions, the empirical loss and population loss, are close at theta star and at theta hat. Then you can bound the excess risk by 2 times alpha. And the proof is actually very simple. What you do is that you know that this is comparing theta hat versus theta star, right? And your condition involves comparing L versus L hat. So you have to do kind of like some arrangement to kind of link them, right? So what you do is you say, I want to compare these two, and I write this as a sum of 3 terms. L theta hat minus L hat theta hat. You first compare this L of theta hat by L hat of theta hat. And then you have L hat theta hat, you compare this with L hat theta star. And then you compare L hat theta star with L theta star. By the way, I don't know why the video freezes up again. Let me restart it. I don't see any reason why this should freeze. Okay. So why you want to do these 3 things, right? It's kind of, once you see it, it's kind of obvious, because this one is the condition, one of the condition, right? This one is the second condition. And this one is the first condition. And you also have this one, which compare directly theta hat and theta star, but this is comparing them at L hat. And you know that L hat theta hat minus L hat theta star is less than 0 because theta hat is the minimizer of L hat. So this term is less than 0, and this term is less than alpha. This term is less than alpha. So in total, you get, if you continue, you get 2 alpha. Okay. So basically, this is saying that it suffices to show the 2 conditions. The first condition is that L hat and L is close at theta star. The second condition is that L hat and L are close at theta hat. So it turns out that the challenge to prove these 2 inequalities are the difficulty are completely different. So let's say if this is number 1, this is number 2. Number 1 is very, very easy to prove, and number 2 will require a lot of work, which takes a few weeks. Maybe not a few weeks, but 2 weeks.
Why in first inequality and possibility and the second inequality is not?
It's just the the only reason is that like of course if you put absolute value here, it's still true, right? And actually you can also bound absolute value if you want. The only reason is that if you don't have the absolute value, to show this set conditions are satisfied, it's a little bit easier, slightly easier. You need one fewer step. That's why in most of the books you don't have that step, and also you save a constant, a factor of 2. So in my actually this is a very good question. In my first time that I teach this, I just have absolute value, and then later in the lecture I have to do additional steps to fix that constant, which makes a little bit like a little bit annoying. Yeah. But fundamentally, you are right. There's no real difference.
You don't run into that problem when you show the first inequality?
You don't run into that problem when you show the first inequality. Yeah, which I'm going to show the first inequality just right now. The first inequality is very easy. And I'll tell you why they are different. It sounds like they are very similar, right? So the difference is that, I guess let me see whether it's ready for me to talk about the difference. Maybe let me not talk about the difference first. Let me first show the inequality 1 and see why it's relatively easy. And so to do that, so the goal is to show 1. And the main tool we're going to use is the so-called concentration inequality. So, and this is in some sense a non-asymptotic version of the law of large number. So it's trying to prove the same kind of things, but in a different language and with a stronger form. So this is non-asymptotic version, I guess, of central limit theorem. And now you don't have to deal with the limit. You just have a bound that depends on it. And I think probably some of you have heard of this inequality called Hoeffding inequality. I think this thing probably is going to be taught in 109, CS109, or some of the statistics class. But anyway, you don't have to know it before as a prerequisite. And let me define the inequality. So this is trying to deal with a sum of independent random variables. So let's say x1 up to xn be independent random variables. And suppose they are bounded. Each of them is bounded by ai and bi. You can think of ai and bi are just constant, maybe 0 and 1. And almost surely for every I. And so we care about the mean. So the mean of this random variable is defined to be xi. It's defined to be mu. And so the central question is how different is the empirical mean from the average, from the expectation, right? So care about how small is this, and this is a random variable, so you have to have a probabilistic statement. So the claim is that the probability that this difference is small is very big. Or alternatively, you can say that the probability that this difference is big is very small. They're just the same. So you get how big it is. It's very close to 1, and the difference from 1 is this exponentially small number. And what's in the exponential is something like this. Okay, so this is the formal statement. Maybe let me try to interpret it a little bit by instantiate it at special case. So if you define sigma square to be 1 over n times sum of bi minus ai square, I from 1 to n. So then the sigma can be viewed as kind of the variance of 1 over sum of xi. This is not exactly the variance, right? Because but it's kind of like some kind of like a upper bound of the variance. Why? Because if you look at the variance over n times the sum of xi, you know that the variance is linear. So so first of all, you get 1 over n squared in front because the variance is quadratic in scaling, and then you have the linearity. So you have the sum of the variance of xi, and then this is equals to 1 over n squared by definition, xi minus expectation xi square. And now because each of these xi is always between bi and ai, right? So xi is between bi and ai, and expectation of xi, as a consequence, also is between bi and ai. That means that this thing, this thing is smaller than bi minus ai, because both of these two quantities are in this interval. So the difference of them is also smaller than bi and ai. You get bi and a square, right? Each of these terms. So that's why the total, the whole thing, maybe I guess also including the 1 over n square. So the whole thing is smaller than 1 over n square times sum of bi minus ai square, right, from 1 to n. Wait, let me see why I'm missing a. I think I have a. I think I have a typo here. Okay, so basically you can think of each of this bi and ai square is the variance, and then you take the sum of them and you divide by 1 over n squared. That's kind of the variance of the whole xi. And suppose you take this view and you can see what this is saying. What this inequality is saying is the following. So if you take epsilon to be square root some constant c times sigma square times log n. So this is something like a constant O of sigma square root log n. So you take epsilon to be something a little bit bigger than the variance by square root log n. Then you know that you plug this epsilon into the Hoeffding inequality, and where c is a large constant. Then you plug in this to the, for example, c is larger than 10. And if you plug in this epsilon to the Hoeffding inequality, what you get is that, so probability 1 over n times sum of xi minus mu. This is actually the most interesting regime of this inequality when you plug in epsilon to be on this level. That's typically when you use it, you always use epsilon to be this level because this is the useful regime. So when you apply it, you get this is less than O of sigma log n, because I replace this by epsilon. It is bigger than 1 minus 2 times exponential. Now let's plug in epsilon. So you get this is 2. Maybe let's first not replace epsilon. Let's first replace sigma, right? So you can see that the right-hand side, by my definition of sigma squared, right? So this is the same as the Hoeffding inequality. And then I plug in epsilon, I get 1 minus 2 exponential 2 log n, 2 times big O of log n. I guess 2 is also in the big O, so you get. Right. So, and now you choose this big O to be a large constant, right? So recall that like this big O is, you can replace this big O by a large constant, right? So then you get this to be something like 1 minus, maybe let's say, I guess maybe here it's easier to, if I just keep the C explicitly, I get 2C here. This is C. Then you get n to the minus 2c, 2 times n to the minus 2c. And if you pick this constant c to be something like 10, then you get 1 minus 2 to the n minus 20, right? So basically this is saying that you have a very, very high probability such that the difference is smaller than sigma log n. So in other words, with high probability, so with probability, let's say larger than 1 minus n to the minus 10, you have that the mean is, the empirical mean is close to the expectation in the sense that they are close in this sense, right? They're bounded, the difference between them are bounded by big O of sigma times log n. So So basically, this is saying that if you think of sigma as the variance, as the code variance, then you cannot be it's very hard for you to deviate from the mean by something larger, much larger than the variance, right? So this is the deviation from the mean, and this is the variance up to times square root log n. Often log factor in this course is not very important, so this is saying you cannot deviate from the mean by a large factor of the variance. Of course, this variance is not a real variance; it's this is perceived variance. Actually, we're gonna get back to this concept. This is sometimes called there's a concept called variance proxy, so which we're gonna talk more about it. So in some sense, it's kind of like if you draw this, it's kind of like you are saying that this random variable, this suppose you call this x hat a random variable. If you look at the distribution of this random variable, it's something like this, and the mean is mu, right? So suppose this is the mu, and you look at something deviate from the mu by sigma square log n, and then you are saying that the mass in this part is extremely small. How small they are? They are smaller than inverse polynomial of n, right? So the mass here is smaller than n to the minus 2c, or maybe inverse poly in n. So, and you can see that this bound cannot be much smaller. So, and one of the ways to see it is that if this is really sigma is really the standard deviation, then your bound cannot be improved much, right? Because for any random variable, you always have some probability. So the bound cannot be improved much. Of course, this is a somewhat kind of like a just intuition, right? Because I need to define what they mean by not improved much. But intuitively, this bound shouldn't be able to improve much, because for any random variable, you always have some mass. There's always some mass within mean plus minus standard deviation, right? So if you really kind of look at the interval defined by the standard deviation, there's always some mass in that, right? There's an actual constant amount of mass in that. So you cannot say that. So you cannot kind of like make this intervals much smaller and get the same bound, because if you get me too small, then you have a lot of mass in it. So okay, cool. So now let's interpret this a little bit more. So let's say we take A and we instantiate even more. So let's say take A to be on the order of maybe -1. It's a negative number, and B is on the order of 1, right? So this is typically the important thing, right? So your random variable is between -1, 1, maybe minus a constant. For constant, then what you have is that the empirical mean minus the expectation is smaller than big O of sigma square log n. This is the same thing I have written. And what is sigma? Sigma is square root 1 over n squared times the sum of bi minus ai square. And this is something, each of the bi and ai is on order of 1. So you get 1 over n squared times n, because there are n of these terms. So this is 1 over square root n. Right. So sigma is on order of 1 over square root n. That's the variance of your mean estimate of the empirical mean. So that's why if you plug in this choice of this sigma, you get square root n square root log n. So basically, you cannot deviate by, and sometimes people write this as O tilde of 1 over square root n, just to hide all the log factors. So if you don't care about the log factors, basically it's saying that you cannot deviate by more than 1 over square root n. And this is something, it sounds very abstract for the moment, but in the long run, you'll see that this kind of thinking will be used many times, and it's actually useful to kind of just burn this in your head if you really do machine learning theory for life, But you don't have to. But for me, this is something like basically I already kind of burned this into my head in some sense. Any questions? Okay, So this is a kind of like a short, kind of like a review. I'm not sure whether how, like, I think probably CS109 doesn't get into this kind of details, but this is just a kind of a review and of Hoeffding inequality with a little bit kind of like additional interpretation. And now if you apply Hoeffding inequality to our case, let's see what we can get to the empirical loss. Right? Recall that our goal is to deal with this, the difference between this and this, right? And this one is 1 over n times the sum of the loss on each of the example. And this one is really literally the expectation of the sum, right? And so this is a perfect case to use Hoeffding inequality because this one corresponds to xi. But Hoeffding inequality requires a bound on a random variable, so we just assume that in many cases the loss is still bound, it's indeed bounded. So, but here we assume the loss is bounded between 0 and 1. If the loss is not bounded, you need a little bit more advanced tools to deal with it. But let's say that for now the loss is bounded between 0 and 1. For example, if you use classification, your loss is 0, 1 loss. The loss can only be 0, 1, so that satisfies this loss. So for every x and y and theta, let's say, then if you apply Hoeffding inequality, what you get is that, so this is a lemma, but actually it's really just the application of Hoeffding inequality. So for any fixed theta, so suppose you, so let me see. So L hat theta, this is basically a sum of xi, right? Where xi is this Lxi y and theta. And so you can compute sigma square, right? The kind of like the fake variance that we are thinking about. So the sigma square I defined was this, bi minus ai square, I from 1 to n. And I guess we have done this 1 over n squared times n, which is 1 over n. So that means that L hat theta minus L theta, right, is less than O of sigma square root log n with high probability, right? So, and sigma is 1 over n, sorry, sigma square is 1 over n, so this is O of square root log n over square root n. And you can also write this as O tilde of 1 over square root n. So basically, for every fixed theta, the empirical loss and the population loss only differ by 1 over square root n with high probability. So sounds pretty good, right? So we show that they are very close, and how close they are close by 1. The difference is 1 over square root n, which goes to 0 as n goes to infinity. So it's supposed to be a small number, and there's no any other things hidden here. Of course, you had a log factor. You had a log factor in n, but you don't have any factor about, for example, dimensionality. Any questions? So, but there is a small issue. Go ahead.
The probability here is like 1 minus 1 over n to some constant.
Yep, yeah, exactly. So with high probability, so technically I should write the probability that this is happening is larger than 1 minus n to the O of 1. Okay, and this is actually a good time to practice this big O notation. Basically, this is saying that you can replace. Actually, here I should wait. Let me see. I think. Should I use omega of 1 and omega of 1? I think I should use omega of 1. But maybe let's say C. Let's say there exists a C such that a constant, there exists a constant larger than 0 such that this is true. Maybe. Yeah, you see, like sometimes this is confusing. Like now I'm on the fly, I couldn't figure it out, but this is what we mean. Maybe let's say, maybe let's just say this is 10. I think this is definitely a correct statement because there is O here. You can hide everything in there. So that's what I mean. Okay, cool. Okay, so this is a correct statement, but there is a small thing that there is an important thing we should note here. So what do I mean by for any fixed theta? What does this really mean, right? I have this header here. So this really means that you need to first pick theta, and then you draw. After you pick theta, you draw IID, right, xi and yi from this distribution P, so that these are well, why you have to do this? Because you want to make sure that L of xi, yi, theta, these are independently distributed, are independent for different i's. So if you pick theta first and then you draw the xi's, then indeed this random variable xi, which is equal to a loss, are independent. But this doesn't really mean that you can do this for theta that depends on xi, which is actually what I'm going to talk about next. So first of all, you can apply this for theta. You can apply this for theta is equal to theta star. That's a lot because theta star is a universal quantity, right? You know what theta star is. You know the theta star exists even before you draw the samples. Why? Because theta star is the minimizer of the population risk. The population risk doesn't depend on the samples. It only depends on the distribution. So that's why you can apply this with theta equals to theta star. So that's why we got this inequality 1, because we got L hat theta star minus L theta star is less than O tilde of 1 over square root 2. So now the question is whether you can apply this to theta hat. And the answer is no, you cannot apply it to it. And it's not only just because you have some subtle kind of mathematical rigorousness. It's really just it's not even correct. It's very far from correct to apply it to theta hat. It's not a small kind of mathematical nuances kind of thing. And the reason is that there's a dependency issue, right? So as I alluded before a little bit. So the dependency is that you first have theta star, right? Theta star depends on the population distribution, and theta star is something that is kind of exists there before even you draw the sample, and then you draw the sample. And then you get theta hat, and then you right, and then you can compute, for example, L theta hat or L hat theta hat, these kind of things. But theta hat depends on the samples, so that means that L of xi, yi, theta hat are not independent with each other. So you cannot apply Hoeffding inequality because they are not independent random variables. So and this is kind of important because if you can really apply this, actually, you always if you can apply this Hoeffding inequality for theta hat, you always get 1 over square root, and there's no dependency on anything. Then machine learning would be much easier. Like we don't have to think about sample complexity. It's always small. So basically the next 1 or 2 weeks we are dealing with this. How do we deal with theta hat, right? So the idea to fix this is called uniform convergence. And the key idea is that you want to apply Hoeffding to any theta that is predetermined before drawing data. Right? You can apply this to any say that it's predetermined before drawing the data. I guess this might sound a little bit kind of like by itself a little bit kind of vague. So what I really mean is that you want to prove that. So what we know now is that for every theta, probability L hat theta minus. So for every theta that has nothing to do with your samples, you know this is true. For some data, of course, I didn't specify exactly what epsilon delta is, but this is the form of the theorem we are proving right now. We can prove right now, and we have proved this for, and you can plug in theta is equal to theta star. That's fine, but this is not the same as for this is true. So the second statement is what I'm going to prove in the next 2 weeks. But these two are two different statements. The second statement is saying that you first draw the samples, and then after you draw the samples for all theta, these two functions are closed. Maybe it's kind of useful to draw a figure, right? So so there is a function called L theta, right? And here this dimension is theta, and the y dimension is the L theta. And now let's look at what's the empirical loss. So the empirical loss, so I guess maybe let me give an example where these two statements are different. So let's think about there are only three cases. So this is a very toy example, right? So consider the case where L hat theta is this function. So it's the right function with probability 1/3. And it's the orange function with probability 1/3. And maybe let's say is the green. This is a sign, I guess, that you have different color. Green function with probability 1/3. And so what you know is that for every theta, so if you for any fixed theta, if you look at the probability that L hat theta is different from L theta, let's say they are just different. So what's the chance that they are different? So this chance is something like 2/3, right? Because if you look at any point, any theta, you know, for some theta actually it's always the three functions are always the same, right? They're always the same. But maybe, for example, if you pick a point here, right? If you look at this point, then with probably 1/3, L hat theta is this right point, which is different from L theta. And with the other two possibilities, right, with probably 2/3, L hat theta is equal to L theta, right? So basically for every theta, you have some, sorry, I should write this is equals to, is a third, right? So basically for every theta, you have something like this, right? Like and on the other hand, if you look at some statement like this, right? So if you look at this, for every theta, L hat theta is close to L theta. Then what's this thing? This is saying that basically these two functions are the same, you know, globally. And clearly, in any of these red, yellow, and green cases, this probability is 0, because in both of these three random cases, right? So the two functions are not always the same, right? There's always some chance that there's some differences. So that shows that you cannot easily switch the probability with the for all quantifier. They are not switchable. I guess, you know, probably you have seen that also like in some sense, some of you probably would expect this. Like this is about union bound, right? Like when you do union bound, there's always these kind of things like whether you can switch the probability with for all quantifier, which we are gonna talk about in a moment. So basically, this is probably, I hope this is demonstrating that it's kind of more difficult to prove that to prove L theta hat minus L hat theta to prove equality 2. So the take-home point is that it's more difficult to prove equality 2. What's equality 2? Equality 2 was the difference between L theta hat and L hat theta hat. And the reason is that theta hat is a function of the data set, and you lose the independence. And so the goal of the many of the rest of the lectures is to show that this is indeed bounded using the so-called uniform convergence. And by uniform convergence, let me just summarize. I hope you got some intuition here already. Like we need to prove something like probability that for all theta hat close to L theta is less than epsilon. Is larger than 1 minus delta. So we need to prove something like this using some techniques. And you will see that you're going to get much looser bound when you prove something like this. The epsilon and delta would be different from the epsilon and delta that you can get when the for all quantifier is outside the probability. So I guess I'll show how to prove this kind of bound in the next few lectures, but just I guess show that this suffices. I guess as expected, if I have a claim 2. So you know that L theta hat minus L theta star is less than, I guess, by claim 1. This is less than the differences between L theta star minus L hat theta star plus L theta hat minus L hat theta hat. And this is less than 2 times the sup over all theta, L theta minus L hat theta. Right. So if you can show that for all theta they are similar, then you have a bound for the excess risk. So maybe just in some sense, if you draw the picture here, so basically what you want to show is that suppose this is the population risk, L theta. You want to show that with high probability, your empirical risk is something like this, which is kind of like uniformly close to the population risk. That's kind of the intuition we have. And actually, let's see. So, yeah. So and actually, if you in the second half of the lecture, like after week 5 or week 6, we're also going to talk about that it's not actually, this picture is actually not entirely accurate in the sense that this picture is accurate in the sense that indeed in many cases the empirical risk is kind of like bounded by some epsilon, right? Within the epsilon, within the population risk, but also it doesn't look like this kind of fluctuating. So what really happens is something like maybe you have a function population risk like this. This is population, and the empirical risk is something, first of all, close to the population risk, but also in terms of the shape and the curvature, it's also close. So it wouldn't be like that fluctuating. It would be something like maybe this. So not only in terms of the value they are close, but also in terms of some other properties, maybe the curvature, the shape, they are also somewhat close. And this is useful for certain kind of like cases when you especially care about optimization, right? So for example, if the empirical risk is so fluctuating, then it becomes harder to optimize. And when you care about optimization, sometimes you want to show that the empirical risk can also have nice properties for your computational purposes. Okay, I guess that's a perfect time, stopping time. Okay, thanks.